Hello everyone, I'm Norman Wahlberg. Thanks for joining me on this adventure where we are trying to bridge the gap between solving polynomial equations and the rich Catalan story in combinatorics. And today this bridge really is going to come into very clear focus for us. So this is actually quite an important lecture. We are actually going to be able to connect these BiTri numbers, this array that we've been looking at quite a lot, and polygonal subdivisions. And it's going to shed light on this fundamental question about why these two things should be related. Why should solutions to a cubic equation have anything to do with these BiTri numbers, and why should these BiTri numbers capture these polygonal subdivisions of a general polygon into triangles and quadrilaterals? So I remind you that the BiTri array is given by this very succinct formula here. CMN is 2m plus 3n factorial over 1 plus m plus 2n factorial, m factorial, n factorial. It's a sub-multinomial coefficient. And our indexing here is starting with m equals 0 and n equals 0, giving us the Catalan column and the Fus row. And today we want to extend our understanding that we've gained in the last few videos on the Catalan story and the Fus story. We want to extend it to this two-dimensional situation. So maybe a first order of business is to actually define a concept that we're talking about quite a lot. So it's nice to have a designated name. Let's agree that a bi-tri-roofed polygon, we're going to introduce that phrase, and what it means, it's a polygon which is subdivided diagonally, the way we've been talking about. So diagonally means joining vertices to vertices, no interior vertices, into triangles and quadrilaterals. And also, there should be a distinguished top edge. We usually put a little bar over that top edge, okay? That's what the roofed expresses. So in the usual language of trees, people talk about rooted trees or rooted polygons, maybe. For us, the special node is not at the bottom, it's actually at the top. So I think roofed, which is just a small perturbation of that, is actually a more apt term, okay? So let's agree to that. Bi-tri-roofed polygons, those are the things that we're considering. And we suspect, we're not sure, but we suspect that these numbers are counting the numbers of such bi-tri-roofed polygons. That's a major conjecture of ours that we would like to establish. We've only really kind of looked at it in this sort of top left-hand corner and rather laboriously checked this out for some special cases. Today, we're going to be able to see a much more general and powerful argument. So watch carefully. It's almost going to be like magic. I'm not actually going to do anything really dramatic computationally. We're just going to think about things in a good way, motivated by what we've been doing with Catalan and Fus numbers, which is ultimately motivated by that exercise in this beautiful text, Concrete Mathematics, by Knuth and Company, Graham and Padashnik. Okay, so we are conjecturing, let's follow down here, we're conjecturing that the numbers CMN, these ones here, give us a power series solution to a general cubic equation, first of all. That's one major conjecture. And the other one is that they also count the number of bi-tri roofed polygons with m triangles and n quadrilaterals, and that necessarily means with 1 plus m plus 2n vertices. So this is really a bridge. This BiTri story is a bridge from the cubic story to this combinatorial / geometrical story involving these subdivided polygons. And the sizes of these polygons that are appearing here might be just useful to contemplate them, all right? So here are the sizes, starting in the top right corner with the degenerate polygon with two sides, okay, which sort of plays a special role. And then we go down by 1 and we go across by 2, okay? So for example, this 10,010 that's sitting here in the sort of third row, starting with 0, so down there in that third row, and in the third column, that counts the number of 11 gons that can be subdivided into 3 triangles and 3 quadrilaterals. Roofed 11 gons. We haven't checked that, okay? Well, that's just the conjecture, but that's what we're trying to get at. So this is like a huge extension, really, of the Catalan story. All right. So how are we going to do this? So what we're going to do is we're going to take our approach that we've been talking about in the last few videos and just sort of extend it in the most natural way. So first of all, we extend the binary and ternary operations to these bi-tri-roofed polygons. All right, so let's grab our triangle symbol. So we are going to take this upside down triangle with a bar on top, and we're going to now define P and Q, this binary operation. It's just what we did before, but I want to write it in a little bit other way because I'm thinking about generalizing this to higher numbers. So let's put something in there. Okay, so this is supposed to be P, and then the triangle, the Q. This is the operation that we were talking about last time. Okay, so this is the binary operation that appends P and Q to the left and right sides of a roofed central triangle. Okay, so we're just introducing a slight variant by putting the operator out in front. Okay, is that all right? So now, and I should say, okay, that this is now, we're extending the story now to bi-tri-roofed polygons, okay, where P and Q are bi-tri-roofed polygons. Okay, so formerly we just had this triangle operation on polygons that were subdivided into triangles. Okay, now we're just observing that this operation still makes sense if you have two polygons which are both subdivided into triangles and quadrilaterals. This one's subdivided into triangles and quadrilaterals. This one's subdivided into triangles and quadrilaterals. Then we take our central triangle and we rotate these things around and glue them to the two sides of the central triangle. The result is another bi-tri-roofed polygon. Okay, and similarly, we're going to take the other operation that we had. Okay, but now it's going to apply not to two bi-tri-roofed polygons, but to three of them. Okay, so and similarly, this is our ternary operation, now extended also to bi-tri-roofed polygons. All right, so this world of bi-tri-roofed polygons supports two operations. We can glue any two of them onto a central triangle and we get another bi-tri-roofed polygon. We can glue three of them onto a central quadrilateral, P, Q, R, and we get another bi-tri-roofed polygon. Okay, so this bi-tri-roofed polygon world is closed under two operations. Let's have a look to see what this looks like more concretely. Okay, so let's have a look at these bi-tri-roofed polygons. They naturally can be organized in an array which exactly mirrors our bi-tri numbers array, but which is more elaborate, in which the entries are not just single numbers, but actually collections or multisets of these bi-tri-roofed polygons. So have a look at this thing here, okay? So in this top corner here, we just have the single degenerate two-sided polygon. As we go down, we see various triangulations, first of a triangle, and then of a quadrilateral, and then of a pentagon, and so on, and we get the usual Catalan numbers. And the numbers in red under the bottom left corner of each little square is count of the total number in that square. So down here at the bottom with the pentagons, there are actually 5 of these, and I've only shown you 2 of them, and then there's 3 dots, but altogether there's 5 in that sort of box. And then if we go over to the next column, go over to the next column here, this one here, that starts with a quadrilateral up on top, and then we go down by 1, we get a pentagon, and the 5 ways of subdividing a pentagon into 1 triangle and 1 quadrilateral. This column always has 1 quadrilateral. So if we go down 1 more, we go to hexagons, and there's the 21 ways of subdividing a hexagon into 1 quadrilateral and 2 triangles. And then below that, the 84 ways of subdividing a 7-gon, I suppose, into 1 quadrilateral and 3 triangles. Okay, and then the next column over here, we're starting with a hexagon, the 3 ways of subdividing it into 2 quadrilaterals, and then we go down 1. What that means, we're adding a triangle. We still have 2 quadrilaterals, but now we have 1 triangle as well, and there's 28 ways of subdividing this 7-gon. Then we go down 1 more. Now we're adding another triangle. So there's 2 triangles and 2 quadrilaterals, altogether 180 ways of subdividing an octagon. Okay, and that's the general pattern. We just keep on adding more and more. So I want you to think about this entire array of these BiTri roofed polygons. Okay, this is an object which is really interesting. In some sense, this is a finer object than the actual just array of numbers. Okay, here we actually have combinatorial objects, and happily, these are combinatorial objects, but we do have some very simple kind of arithmetic that we can do with them. Like what? Well, we can form a binary operation on any 2 of them. That's our triangle operation. And if we have any 3 of them, we can perform our ternary operation. Okay, so let's just illustrate that. Okay, so the binary operation, let's grab 2 of these things. So maybe I'll grab this one here. Okay, and put the top on top, and maybe where's another one? Maybe hexagon with that one there. Okay, there's the top. Okay, so those are 2 things, and I'm going to put the operator on the left. Okay, so what's that do? Well, I think we all know. So there's a triangle in the middle, and then we have to stick the quadrilateral on the left-hand side and just make sure that the top is sort of being glued along there. So I have to tilt my head, and I guess I have to put the diagonal in like that. And then in terms of the hexagon, well, we have to glue that on here. So there's the hexagon with the top, again, glued there, and then the other stuff is there like that. Okay, clear? And then we could rewrite this if we wanted to. It's going to be a 1, 2, 3, 4, 5, 6, 7, 8, 9 gon. So I guess I could write this 1, 2, 3, 4, 5, 6, 7, 8, 9, something like this, where there's a distinguished thing, and there's going to be a triangle, 1, 2, 3, 1, 2, 3. So there's going to be a quadrilateral on that side, and then there's a triangle, and then our hexagon on this side, and then we have to put the diagonals in like this, and I suppose like this. Okay, with a distinguished roofed top there. So that's an example of taking 2 arbitrary BiTri roofed polygons and performing this triangle operator and getting another BiTri roofed polygon. Okay, it's a happy situation because it's essentially like an algebraic structure, but it's taking place in this world of these funny BiTri roofed polygons. And it's important that they're roofed, right? If they weren't roofed, we wouldn't be able to do this. There would be a question of, well, which side are we going to glue in? But they all have distinguished tops, so that makes it easy to know where the gluing takes place. Okay, and then there's also the ternary operation. Ternary operation. Let's just review that one. Okay, so now we're calling it a square or quadrilateral. And okay, so maybe I'll take this one here, And maybe I'll just use the degenerate one just to make life a little bit easier. And over here, I'm going to put a triangle so I don't have to work too hard, okay? So I'm going to multiply those three things. So how do I do that? Well, I take our central thing is a quadrilateral. On the right-hand side, I have to put this one here. So I'm going to put a quadrilateral over here, glue it along that edge, and put the side there. Then our degenerate quadrilateral is going to end up being glued at the bottom here. So it's basically effectively not doing anything. You're just sort of gluing an edge to that edge, so nothing's really changed. And then on the right-hand side, we're gluing a triangle with its edge like that. Okay, the effect is to have a 1, 2, 3, 4, 5, 6, 7 gone. 1, 2, 3, 4, 5, 6, 7 gone. And there's a quadrilateral on this side, so I guess it's like this. Okay, and here then there's going to be a side like that. Okay, and there's the top. Great, okay, so those are our binary and ternary operations. Okay, and now we're going to do the same kind of thing that was suggested to us by Graham, Knuth, and Patishnik, okay, in that exercise 22 in chapter 7. We are going to take the multiset of all of these BiTri-roofed polygons, and we're going to give that a name. So let's let A be the entire multiset, okay? A equals, I might say. So if A is the entire multiset, M set of BiTri-roofed polygons, then we're going to write down an equation satisfied by A. Every element in A is one of three kinds. Either it's just the degenerate two-sided thing, which is just the single thing in the top left corner. That's a kind of special case. Or it's one of two other possibilities. So if you have some big polygon, okay, and here is its top edge, then that top edge is going to be part of a constituent polygon, which is either going to be a triangle or a quadrilateral if the starting thing is not itself the degenerate two-sided thing. Okay, so we're either going to have a triangle somewhere, or we're going to have a situation where this this top edge is somehow related to a quadrilateral. So either a triangle in the center or a quadrilateral in the center. Now, what that means, in the first case, if there's a triangle, then that means that you can write this thing as essentially the product of a P and a Q, okay? And what that means is that every element in this multiset is of the form triangle. Every such element that has a central triangle is of the form triangle of some element in A with some element in A. Okay, so no matter which two elements in A you choose to be P and Q, you can create this binary product, and you're going to get a new BiTri-roofed polygon. And every BiTri-roofed polygon which has a central triangle is going to be of that form. But there's also the ones that are of this form, that have a central quadrilateral, and they're going to all be of the form, well, something like this, where here there's a P, and maybe here there's a Q, and here there's an R. Okay, so they're going to be it's going to be of the form quadrilateral product of A with A with A. This is an identity of multisets. And it's really important to get your head around this identity, to convince yourself that this is going to be the case. What we're doing is we're going a little bit beyond concrete mathematics here. In problem 50, which I've also mentioned, of that text, which is very interesting. It's some kind of generalization of the Catalan story. But they're suggesting something that I don't really know how to do. They're also making an extension to more general subdivided polygons, but I don't really know how to answer their problem. What I'm doing here is something a little bit different. I want to use both operations, okay? Because there are these two possibilities for that central polygon. Either it's a triangle or it's a quadrilateral, or it's not there at all, and we have this degenerate two gone. Okay, so I'm using both the binary and the ternary operation, combining them both to get this identity that A satisfies. A is the entire M set of BiTri-roofed polygons. All right, great. Okay, so once we've got our head around that, what are we going to do? Well, what did we do last time? In both the Catalan and the Fuchs stories, what we did is we tried to bring this abstract algebra of M sets down to earth a little bit by connecting them with polynomials. Okay, we introduced this phi. And in the triangle case, phi sort of counted the number of triangles. It was a little polynomial with t to the n, where n is the number of triangles. And in the Fuchs story, we were counting quadrilaterals, and we associated to such a thing a little monomial q to the something, where the something is the number of quadrilaterals. Okay, now we have to combine those two things because we're in this two-dimensional situation. So let's extend our phi mapping from now these BiTri-roofed polygons to polynomials in two variables, t and q. Okay, so what's our definition going to be? So phi of, let's say we have some BiTri-roofed polygon P. Then we're going to define this thing to be t to the, let's say, m and q to the n, where P has m triangles and n quadrilaterals. All right, so for example, fine, let's make up, I'll say maybe something like this. Okay, there's a triangle, there's a quadrilateral, there's another triangle, there's a quadrilateral. Okay, there's the top. Okay, what is phi of this thing? Well, we count the number of triangles. There's one there, there's one there. So we have to put t squared. And now we count the number of, sorry, that was sorry, wrong. That was the triangle there. There's two triangles. Now we count the number of quadrilaterals, one right there and one right there. So two of them. So we put in a all right, so what properties is this going to have? This is going to have two crucial properties. Sorry. It's going to have two crucial properties. That if we take phi of the triangular product of P and Q, okay, what are we going to get? We're going to get phi of P. That's the number of the monomial of that counts triangles and quadrilaterals in P, times phi of Q, that's the monomial that counts triangles and quadrilaterals in Q. Okay, and they're going to multiply together so that the powers add. So we're effectively just adding the number of triangles and the number of quadrilaterals, but separately. But in addition, there's also this central triangle that's part of the construction. So we're upping the number of triangles by one. We have to put a t in front. Okay, that's the first property. So phi of triangle of PQ is t times 5p times 5q. And the second property is that phi of square of P and Q, well, you're still going to have all the triangles and quadrilaterals that P has, and you're still going to have all the triangles and quadrilaterals that Q has. But now in addition, there's now an additional central quadrilateral, which ups the number of Q's in the expression. So we have to put a Q here. So when we apply this to our basic fundamental identity, let's say star, we get well, let's let phi of phi of A be, let's say, F. Okay, so this is going to be a multiset, an M set of monomials. You know, the form T to the something, Q to the something. So what happens when we apply this phi mapping to this? Okay, so let's start with A equals this sort of identity kind of fellow times triangle of A plus quadrilateral operation on A. What we're going to get is that this F, which is just the image of A under this mapping. So what is that actually? So that's what you would get when you go up to this diagram here and you replace each one of these polygons with a monomial. Okay, like this one here would get replaced with Q, because it's one quadrilateral. This one get replaced with Q squared. This one get replaced with Q squared. This one gets replaced with Q squared, etc. This one gets replaced with there's now three quadrilaterals, so it'd just be Q cubed. There'd be these 12 Q cubes, etc. Okay, down here we got I guess one triangle and 2 quadrilaterals. Each one of these would get each of these 28 would get replaced with TQ squared. There'd be 28 TQ squareds in that box, which we could then just write as 28 times TQ squared. So we're going to get sort of an infinite or an ongoing polynomial in T's and Q's. Okay, the image of this M set under this phi mapping. Okay, and that's F. All right, so now what is the claim here? That this F, which is the left-hand side, is going to be what on the right-hand side? On the right-hand side, well, the image of this identity thing is just 1, because there's 0 triangles and 0 quadrilaterals, so T to the 0, Q to the 0 is 1. Okay, what about this thing here? A times A. So we're multiplying each of the elements by A, and each one is getting multiplied in addition by this triangle operation. So exactly the same reasoning that we applied in our Catalan story tells us that this is going to be T times F squared. And exactly the same kind of reasoning that we applied in the Fus lecture. We've got A's all multiplying in all possible ways. That's essentially giving us an F cubed. But all of those terms are going to have this additional Q in front of them, because the square or the quadrilateral operation always gives this additional Q as up here. So we're going to get Q times F cubed. That is a cubic equation in F. A cubic equation. And that, ladies and gentlemen, is, I think, why there is this intimate connection between cubic equations and these polygons. It's exactly for this reason. This is a geometrical explanation of this connection, that these polygons and the way they multiply are naturally inducing this sort of generic cubic equation. Now, it's not entirely generic, because the constant term happens to be 1 and the the coefficient of f is actually, if you bring it to the other side, is -1. But, aside from that, the t and the q are kind of general, aren't they? So it's pretty close to being a general cubic equation. And so now we can sort of see why it is that our cubic equation story ended up with something in this direction, because there's this natural connection between them. But we can do more with this. We can now go back to our BiTri array and see if it actually does satisfy this equation. And if it does, that will basically confirm for us that our BiTri numbers really are counting these BiTri-roofed polygons. All right, so now I want to see if this BiTri array really does generate a function f, or sort of a polynomial f, an ongoing polynomial f, that satisfies that cubic equation that we just wrote down. Okay, so what I'm going to do is to create the polynomial is I'm going to multiply our array here. We're just going up to this case 1, 2, 3, 4, 5. I'm going up to m and n equals 5. And I'm going to multiply by this vector 1t, t squared up to t to the 5th on the left, and by this column vector 1q, q squared down to q to the 5th on the right. And when I do that, let me just expand what we get. All right, I get this, this thing here, okay? And let me actually give it a name, okay? Let's call it f. F equals. Okay, so it's going to have, this is some expression that has, I guess, 36 terms. Okay, let me just expand it out, just compute, expand. There's the 36 terms, right? Each one of them corresponding to an entry in this table. And of course, this is not the entire BiTri, right? This is just the top left corner, okay? But so we're just kind of going up to degree 5 and ignoring higher degrees. Okay, so let's make this definition. So let's get rid of that, and we'll make this definition. First of all, let's clear our definitions. Definition's clear. Now we'll make this definition. And now let's have a look at what's the equation that we want to satisfy. The equation was f equals 1 plus t f squared plus q f cubed. Okay, it's an equation involving f and the variables t and q, which are involved in f. We want to ask, is this actually true? At least up to terms of degree 5 in both t and q. Okay, that's a really good question, isn't it? Okay, so what we're going to do is we're going to take, let's say, take the right-hand side here, 1 plus t f squared plus q f cubed. Now, if we just expand this out, we're going to get all kinds of additional terms, because we're going to get lots of terms which are of degree higher than 5 in q and t. So the way I'm going to cut that down, I'm going to do it in 2 steps, because I can only have to do it in 2 steps here using this program. So power series. So let's expand this out. Number of terms, maybe 6. Let's say in terms of q. All right, expand this out in terms of q. And now I'm going to compute, expand this out. Okay, get rid of this O. This O just means that there's higher degree terms. And now I'm going to cut out all the t terms which are higher. So power series now in t. Where is it? It's down here. Okay, so this is what I get. Get this thing here, and plus O t to the 6. Let's expand this out. Get rid of this and compute, expand. All right, so that thing there. That's what we got, right? That's what the right-hand side. And now I'm going to set this equal to f. So I've taken the right-hand side, I've expanded it out, I've chopped off all terms of degree higher than 5 in both t and q. I'm hoping that this expression that I have in front of me is actually equal to f. And I can do that by going to compute and check equality. Ladies and gentlemen, it is true. At one stroke, we establish that these numbers that are appearing here really are indeed what we think they are. Because, let you think about it, there's really kind of a uniqueness here. Once you have this thing satisfied, and you know that the first row and the first column are what they should be, then there's a kind of a uniqueness to everything. So what this actually does convince us is that at least up to 5, okay, all these terms that we see here in this array, they do really count the number of bi-tri-roofed polygons of the appropriate size. This 10,010 is no longer just a conjectured number of 11 gons with, I think, 3 triangles and 3 quadrilaterals. It is now confirmed. We have computed and checked this. Okay, I want you to appreciate how efficient this is, right, compared to try to count these things directly. And basically, we've just used some sort of soft thinking. We've just exploited the algebraic structure of this M set of bi-tri-roofed polygons. And we're quite excited because we can imagine ramping this up quite considerably.